Hello, students. We're talking about volume of spheres today. What's a sphere? And you might ask a little kid, ew, what shape is that? And they might say circle. But we're older and our brains can see this as actually a three-dimensional representation. So these actually represent spheres. I really like this one because what does geometry mean? There's two definitions. One is a language used to talk about shapes and their relationships, and the other is geometry, measuring the earth. So it's kind of fitting that this is our last lesson, because we've been talking about measuring things on earth. And a sphere, the earth can be modeled as a sphere, so we could actually measure the earth itself. But what is a sphere? What's a circle? You remember? If this is a point and we have a point next to a point, 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 that's going to create a circle. So a circle is a set of points equidistant from a center point on a plane, on a flat surface. But a sphere is the set of all points equidistant from a center point, kind of in any direction in space. So you can think of it, it's a set of points around a center point. So that's what it is. A sphere is the set of points equidistant from a center point. I'm going to put the set of points in space, in three-dimensional space, equidistant from a center point. So there's only one measurement that you need on a sphere, and that is its radius. So the radius is the distance from the center to any point on the sphere. It could be out this way, that's going to be the same. It could be kind of out to this point out here on the sphere. All of these are all the same measurement, and they're all the radius. Okay, so what's the only important measurement on a sphere is the radius. If we have the radius, we can calculate everything else. And so these are all spheres. What's this one? You could say it's half a sphere, but the word for it that we usually use is hemisphere, which just means half a sphere. Do you guys know the volume for spheres? You know a volume formula for spheres? And we're going to watch this video together and see if you can understand what's happening here.
Video will demonstrate the ratio of volume of a cylinder and a volume of a sphere.
So
we have a cylinder and a sphere with the same height and diameter. Fill the cylinder with water. And push the ball into the cylinder. The volume of the water left in the cylinder is a third of the original volume.
It's a third of the original volume. How much spilled out into the pan?
That means the volume of the sphere is 2/3 of the volume of the cylinder.
She fills the sphere and pours it back into the cylinder. It's gonna the 1/3 was in there. What's she pouring? Okay, that was good. So what did that show us? That showed us that the volume of the let me add a slide here. I'm gonna go right here. Okay, so we had the sphere and we had the cylinder. And what she told us is that the height of the sphere was equal to the height of the cylinder. Okay. And this is a sphere, like an eyeball. And do we know how to find the volume of a cylinder? Okay, when she pushed it in, 2/3 of the water spilled out. Okay. They had the same radius. That was important. They had the same radius and the same height. And when the water spilled out, this is the water spilling out, a little puddle of water here. Okay. 2/3 of the water spilled out because after that there was 1/3 left. So we know that the volume of the sphere is equal to 2/3 the volume of the cylinder. That's what we found out. Do we know a formula for volume of cylinders? Yeah, we learned that a few days ago. The volume of a cylinder is pi r squared h. Okay, pi r squared h. So the volume of the sphere is going to be 2/3 pi r squared. What's the height of the sphere? That will tell me the height of the cylinder. Now I just said for spheres, we only need one measurement, which is the radius, but how does that tell us how high it is? Well, let's look at it. The height, I'm going to draw it this way, is here to here. That's the radius, isn't it? How about this? Isn't that also a radius? It is. So what's a radius plus a radius? Isn't that 2 radiuses? It is. So the height of the sphere is 2 radii, or a diameter, but we're going to use radius. Okay, so the height of this is also 2 radiuses. So 1, 2 radii is the height. Okay, so I'm going to replace this with 2 radii. You know, I'm going to do some math. So the math is, I'm going to multiply 2 times 2, which is 4. I'm going to multiply pi times r times r times r. So that's going to be pi r cubed. Oh, and we need this third in here. It was 1/3 the volume. So the volume of a sphere is 4/3 pi r cubed. That's one way to look and come up with the formula using an experiment. There's another way to think about the volume of a sphere. So here's the formula, 4/3 pi r cubed. Cubed, that's interesting. There's only one measurement in the sphere. So if you need cubes, you're probably going to do it times itself, right? So the cube kind of makes sense because we're talking about volume. Another way to show why this is true is to use Cavalari's principle. This is a little bit more advanced and complicated to think through, but it's a more mathematical and algebraic proof. The way that this one works is, and this is really what we should be doing in a geometry class, is understanding the derivation, where it came from, where the formula came from, mathematically speaking. So the way that this argument works is that they look at a hemisphere related to a cylinder. And, excuse me, and they set it up so that the height is the same. And instead of being 2 radii, the height is just 1 radii. And they compare the cross sections of the circle at the same height. And right now, this circle and this circle don't have the same area. This is a plane cutting through the hemisphere and the cylinder. The cylinder is going to be bigger than this circle slice, because this circle slice is missing, you know, if it was out here, it'd be kind of missing this part out here and this part out here. So right now, this circle is bigger than this circle. That's kind of important to understand. At the bottom, and if you're interested in this, you want to push yourself to really go deeper with these topics, this is a really good activity to look at. So at the bottom, the cross sections are equal. The area of this circle and the area of this circle is the same. But as you move up, this circle is smaller than this circle slice. So something that's really smart is, do you see what's inside of here? There's a hole inside of here. Okay, because as you go closer and closer to the top, you have less and less of a circle. You have some of it missing. So some really smart people figured out that the area of this smaller circle is the same as the area of this disc, of this circle with the hole in the middle. So the next thing they did for this argument was to draw in some more things. So what this is showing is that the area of this circle is equal to the area of this disk space. So it's the area of the circle minus the area of this circle. Now let me show you, for those of you who are trying to understand this at a deeper level. The area, so we're trying to show that the area of this is equal to the area of this like ring, essentially. So I'm trying to prove to you that the area of the circle in this one is equal to the area of the ring. Okay, so let me prove it to you. The radius of this circle, so for the area of a circle, we need pi r squared, right? So what is the radius of this circle with height h? And remember, at the bottom, they're the same, but as it goes up, this small circle is getting smaller and smaller and smaller. At the very top, the circle turns into exactly 1 point. Okay, so as we get closer and closer to the top, this circle gets smaller and smaller and smaller. And this ring has more and more of a hole in it. So let's see, what is the radius at any given height? For that, you have to look at this right triangle. And the radius that we want for this formula is going to be right here. We have the height that's changing, and we have this radius, which is constant. This is a right triangle. And do you guys remember a squared plus b squared equals c squared? It's the right triangle theorem. So for this, we have an h squared plus the thing we're trying to find. Maybe I'll call this question mark squared equals, this is our question mark, equals r squared. Solving for the question mark, we would get the question mark squared is equal to r squared minus h squared. And I take the square root of both sides. Yeah, r squared minus h squared. And that's how long that radius is. Okay. So this radius, it's kind of ugly, but that's what it is. It's the square root of r squared minus h squared. And I can write that in here, the square root of r squared minus h squared. All right, now here's the cool part. we are going to put that radius into here and square it. Well, it's squaring a square root. It's kind of inverse operations, right? So, oh, I'm a little messy. This is going to come over here. This is going to be pi times r squared minus h squared. That's the area of this circle, because it's pi r squared, and this was the radius that we wanted. The radius that's changing in relationship to the height. Right, let's do the area of this circle. So this is going to be, sorry, the area of this sort of this disc shape. This is going to be the pi r squared minus, we're going to take out that center circle, pi r squared. I'm going to take the big circle minus the small circle. Maybe I'll call these radii 1. Okay, and then this is going to be radius 2 of the little circle. And I'm going to call this is radii 1. I'm going to call this is the third radii. And that's the one I need here. But what's really cool is that this radius is also the height. Okay, so here's the magic. Here's where the magic happens. The pi r squared minus pi, what's the radius I just told you? I told you it's h. I told you that this little radius is the same as the height going up. Okay, so we're getting closer. The area of this slice is this. And what's going to happen here? Do you guys see it yet? What do these both have in them? They both have pi. So we've been practicing this a little bit. We're going to factor out the pi out of both terms, and guess what? They match. So someone really smart figured out that the area of this slice of a hemisphere is equal to the area of this disk, this ring. And this is algebraically why that's true. Okay, after they did that, so here's a little bit more of what we just had in that last slide. After they did that, they said that the Cavallari's principle says that the volumes are going to be equal. So if I can find the volume of this situation, that will tell me the volume of the hemisphere. Oops. I think I'll do it here. So let's try to find the volume of, and what we're finding the volume of is we're finding the volume of kind of all of this. So we're finding the volume of all of the disks added together. So I'm going to work on that. The volume of this situation, find the volume of this, and you will know the volume of this. So the volume of this is pi r squared h minus 1/3 pi r squared h. Because we're subtracting the cone out of the center of it. So the volume is, I mean, there's a lot of ways to do this. I'm going to just say 3/3 pi r squared h minus 1/3 pi r squared h. 3/3 is 1. So basically we have 1 full cylinder minus the cone inside of it. And that's going to give us 2/3 pi r squared h. All of this part matches, so we can combine these like terms. All right, so that's it. The volume of this situation is equal to the volume of the hemisphere. Now we know the volume of the hemisphere. I hope this is interesting. I hope this is making sense. It's a little complicated. This is a really fun tool that you could play with to prove it to yourself, kind of work it through a little bit more. But we don't want the volume of the hemisphere. We want to double it. So what's 2 times 2? We need the whole other half, right? So if I want to find the whole thing, I'm going to double this because I know 2/3 pi r squared is half of it. So double it is going to be 4/3 pi r cubed. This is another way to show it. How come I don't have a cube here? Oh, because the height is the radius. Okay, so all of these are going to be radius. It's going to be a radius. Okay, I can go back and put a radius here instead. It doesn't change anything, except it looks more like the formula that I want. So that could be a radius, and that could be a radius, because we set it up that way. And then this is going to be 2/3 pi r cubed, because the height is defined as the radius. The height is the radius. Okay. Double it, and we have our formula. So the formula is times 2 equals 4/3 pi r cubed times 2 for the whole sphere. 2 times 2 is 4. That's why it's 4/3. All right, I hope that was interesting to you. That's where it came from. I showed you 2 different ways with the water and with using Cavalari's principle. And now let's just use the formula. It's really nice. There's only one number we have to deal with. We know the formula now. The volume of a sphere is 4/3 pi r cubed. I'm going to say this is centimeters just for the heck of it. Volume is not length times width times height. Volume is, depending on the shape, has different formulas. The volume of this sphere happens to be 4/3 pi. The radius is 9 centimeters. We're going to cube that. And now we're going to be careful with our fraction work and our multiplication, not to make any mistakes. So I'm going to use order of operations, and I'm going to do 9 cubed first, which is 9 times 9 times 9, which is 729. And if I do centimeters times centimeters times centimeters, that's going to be centimeters cubed. There's lots of ways to do this problem. You could multiply by 4 and then divide by 3, because this is over 1. So you would multiply the numerators together and then divide by the denominator. Or you could divide by 3 first and then multiply by 4. I'm going to multiply by 4 and then divide by 3 because I have a calculator. That's going to give me 972. I still have the pi and I still have the centimeters cubed. And we write it in that order. We write the whole number and then the irrational number, which is pi, and then the units. And the approximate answer for that, I could multiply by 3.14159, blah, 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 or I could use a pi button. And that would tell me this is about 3,050, I'm at around 53.6 centimeters cubed. That's kind of big. That's a lot of cubes that are going to fit in there. But I did 3,053. There it is. Okay, so it depends on the situation. Math people generally like the exact answer, but if you're building something or manufacturing something and you need to know how much material you're going to need to build this thing, you would need to do the decimal approximation. Let's do this one. This one's kind of weird. It gave you the give you the radius in pi, which is just kind of weird, but it's okay. The volume of the hemisphere is going to be half the volume of the sphere, right? So for this one, the volume of the hemisphere is going to be half times 4/3 pi r cubed, cubed because we're doing volume and we have cubed. The radius in this one is pi. So this is kind of a weird problem. So what's half of 4/3? Half of 4/3 is 2/3. Or you could say 4/6, but 4/6 is the same as 2/3. Okay, and I'm going to substitute pi for my radius because that's what it said. And I put units in here because units are good for us. Help our brain think through, help the science teachers give you a little bit more number sense. So the volume of the hemisphere that was shown there is 2/3 pi. This is going to be pi cubed times pi, which is pi to the 4th inches cubed. That's a weird answer, but that's what it is. If I wanted to find what that is, I would do pi times pi times pi times pi. Pi to the 4th. Let's see if I have a pi button. Pi to the 4th. Pi to the 4th power. Wow. Times 2 divided by 3. Okay, I got about 64.9 using my pi button. So 64.9 cubic inches would fill that hemisphere. I'm just kind of checking it. Okay, times 2. I messed up my calculation. Someone can check that for me. If I'm wrong, you can put it in the comments. Ooh, extra fun, solids. So the volume of this, I don't know, it looks like a silo or something. Maybe you're going to store some grain in there. Maybe you want to be a farmer when you grow up. So the volume of the composite, well, what's it made of? You can add volumes together. So it's the volume of the cylinder plus what? Volume of a hemisphere. It's stuck on top of it, like an ice cream. So the volume of the composite solid is pi r squared h plus half 4/3 pi r cubed. All right, do we know the radius and the height? Do we know the area of this circle? Well, be careful. The radius of this circle is 1. Okay, so I'm going to do the volume of the cylinder first. And that's going to be pi times 1 meter squared times 3 meters is the height of that cylinder. And then I'll work on this part. So I'm going to do again, half of 4/3 is 2/3. Pi, what's the radius of the sphere up here? What's the radius of this sphere? Well, it's also 1, isn't it? Because it's the same as the radius of the base. So 1 meter. So this is going to be, oh, it's so nice when it's 1. Okay, so this is, you can see meters times meters is meters squared. So pi meters squared is the area of that circle times 3. So this is going to be 3 pi meters times meters times meters plus we have 2/3 pi times meters times meters times meters. Okay, can we add that together? Yes, we can. So I'm going to get a common denominator. I'm going to change this to 9/3. What's 9 divided by 3? 9 divided by 3 is 3. So I can replace 3 with 9/3 and get away with it. This part's matching now. So now I have a common denominator and I can write my answer as 9 plus 2. 9/3 plus 2/3 is 11/3 pi meters cubed. All right, this is the best answer. The volume of this composite is that. Could you put it as a decimal? Yes, you could. If this was a grain silo and you wanted to figure out how much grain you could store in it, then you would definitely have to get it as a decimal. Ooh, last one, so fun. This should remind you of something of the video we watched. What did we do? We dunked a sphere inside of a cylinder. If the height of the cylinder is equal to the diameter of the sphere, what's the volume of the space between the sphere and the cylinder? So when you dunk this and all the water falls out, what's the volume that's left? If you really understand the video, you don't really have to do very much work for this one. Okay. This is going to be the diameter, which is 2 radii. Do we know the radius? Radius is 12, so this is going to be 24 centimeters. You can see that if this went straight up to the top and straight down to the bottom, you can see that this from there to there, or the height of this cylinder is going to be 24 centimeters. Okay. So if you didn't remember the video, you can still do this problem. The volume of the space between the cylinder and the sphere is the volume of the cylinder minus the volume of the sphere. So the volume of the space between is going to be the volume of the cylinder, which is pi r squared h, minus 4/3 pi r cubed. Volume of the space is going to be this is 2 radii. So there's 2 ways to do it. I think I'm going to do it this way. So I'm going to start with the formula, and then the end I'll plug in the answer. Just kind of bring it full circle. Get it? Full circle? Haha. Okay, so this is going to be 2 pi r cubed minus 4/3 pi r cubed. Do you see how pi r cubed and pi r cubed match? So I could trade this out for 6/3. What's 6 divided by 3? 2. What's 6/3 minus 4/3? 2/3. I feel like I'm making a mistake somewhere. I'm not really sure where it is. Isn't it 1/3 should be left? I thought it was 1/3 that should be left. 2 r where's my mistake, you guys? 4/3 pi r cubed, pi r squared h minus 4/3 pi r cubed. Space between the sphere and the cylinder. This should be 1/3, so I made a mistake somewhere. Oh, this is just, I see it. I made a mistake right here. This is 2 . No, 6 divided by 3 is 2. Volume of the cylinder minus the volume of the sphere. Cylinder is, this is 12. Pi r squared h is 2r. 4/3 pi r squared 6. I got myself confused again. Because I thought 2/3 is the volume of the sphere, but I want whatever's left over. So it should be 1/3. Because 2/3 is going to spill out. I can't find my mistake at the moment. That's a good challenge for you guys. So see if you can figure it out. And I'm going to leave you with that challenge. If you got it, you can record a Flipgrid and show me. That would be awesome. Okay, have a great day, you guys. Be good, work hard, keep learning, keep pushing yourself, and bye.